We're now ready to tackle our last subject for the semester, which is path planning. So the goal for today is to give you a definition for path planning and then consider an example that we'll work through a few times with different algorithms. We'll talk about some of the practical considerations for path planning, talk a little bit about obstacle avoidance. We'll cover a couple of the main algorithms, specifically some graph algorithms like BFS, and then a sampling algorithm called RRT. And then I'll briefly mention how this relates to another subject called localization and mapping, or if you've seen the acronym SLAM, the initialism SLAM, the acronym SLAM, that's what it would be sort of the next step if we were continuing forward. So the goal for path planning, or I'll call it simple path planning here, because we're not going to tackle the harder problem of simultaneous localization and mapping, is you're given a map, which I'll mark here as just optional, just to remind you that we can actually do this without a map, but we will not be doing so in this class. You're given a map, a start location, and a goal location, or in this case I'm calling them positions, because we're not going to care about a full pose. So if you remember, our poses were X, Y, and theta, meaning we were going to care about the orientation of the robot too. Here, we'll just use simple position control and not worry about the final orientation. So that's what you're given. And then the problem that we will look at some solutions to is to find a, first of all, safe, second of all, feasible, and third, continuous So we're looking to find a path from the start to the goal location, and what I mean by safe is that we could define some boundaries, like we're not getting too close to obstacles. Feasible is just a little more strict on this same concept, meaning we're not allowed to drive through obstacles and we have to consider them. Continuous just means that for every location on the path, there's a possibility from going from one to the next. There's some way to go from one to the next. We're not requiring the robot to jump some discrete amount of distance to complete our path. That might seem a little obvious, but there are some path planning problems that don't have that guarantee. Some algorithms. In the space of mobile robotics, we'll pretty much always have this continuous requirement, so it's a little redundant to mention. But since this is an introduction to mobile robotics, and some of you might be interested in getting into different robotics areas or path planning areas, it's worth mentioning. Just as we talked about in the previous lecture talking about simulation, a key thing for us to consider is what is the appropriate level of abstraction for our task. So hopefully this isn't too hard to see, but this is supposed to be Edmonds. Oh, that's hard to read here, isn't it? Go with a different color. So this room here is supposed to be Edmonds 105. And the first question we would need to answer is it really useful to have this in a sort of full three-dimensional space if I'm trying to get a robot to come from, for example, this location to behind these chairs after the third row? And maybe for a drone, we would want this full three-dimensional representation of Edmonds 105. But for what we'll do in this class, it's really enough to just think about this in the more top-down version. So I could start here and find some path to another location over here behind that third row. So always worth asking yourself what level of abstraction is useful, and we will be using a simple grid-based abstraction, really just a two-dimensional plane, a top-down grid. So our version of Edmonds will look more like this. And in fact, some of this detail is superfluous. We don't really need to know the shape of the chairs or that there are monitors on some of the desks and laptops on the others. Instead, we'll picture Edmonds to look more like this. So in this picture, you can think of the green space as being the free space. And we didn't have to break it down this way, but I have two different colors for obstacles. The sort of orangish colored blobs are the chairs, and the more purpley colored blobs, hard to see that it's purple when I'm using opacity here, are the desks. In this case, we'll really just treat chairs and desks in the same way, so we don't really need to differentiate between the two, and our algorithm actually won't. But for the pictures that you'll see throughout these slides, that's what those different colors mean. So now we're left with the question, how do we plan a path? So if we're at this start location, and we have some goal location, how do we make our robot go from one point to the other? Well, currently as it stands, if we were to use our position controller, our robot would beeline directly toward the goal, and it would hit a bunch of different obstacles along the way. So instead, we need some way to let it know about these different obstacles so that it can find a better path. And so to figure out a solution to this problem, we'll talk about a few different practical considerations with path planning. First of all, do we actually need a full path? Do we have some simpler way to get from point A to point B? We'll talk about something called a configuration space, which for us will pretty much be the same Our configuration space will pretty much be the same as our physical space. There are some times when that won't be the case, and I'll make sure to point them out when we get there. Like I said before, we also want to take into account safety bounds. How close to an obstacle are we allowed to get? And then finally, we'll talk about different ways for representing our maps. After that, so this is sort of our interim part, we had our intro, our practical considerations here. Then after that, we'll talk about our algorithms that actually solve this problem. So let's start with this no path path planning algorithm. There are a series of algorithms really called bug algorithms because they're supposed to be simple, basically like what a bug might do, an ant, if you imagine it crawling around on the floor. And instead of our ants sort of having a random walk like they generally do until they build up pheromones to have a path, ours will do something like, for example, if this is our start location and our goal location is over here, they'll be a little more directed. They'll try to beeline for that target. Now they're going to need to be able to sense the fact that there's an obstacle here to get around it. So let's talk about a few different algorithms. This first one is usually known as bug 0. It's kind of the most intuitive way to code up or look at a bug algorithm. So how does it work? You move forward toward the goal until an obstacle is detected. So this does require us to have an obstacle, some way to detect obstacles, which we won't have on our robot. So as you might imagine, we're not going to be implementing bug algorithms. So in some ways, they're more difficult because you have to have those sensors. In other ways, they're easier because there's no actual planning that needs to be involved. We don't have to use breadth first search, A star, or RRT like we'll talk about later. Or actually, I suppose, you don't necessarily need to know have a way to detect the obstacle. You could just know when you're close to it by having a map, for example. But typically we think of bug algorithms as having some way to detect obstacles and reacting to them. So for bug 0, you move toward the goal until an obstacle is detected. So starting here, move to the goal, obstacle is detected. Then you follow the contour of an obstacle until motion in a straight line toward the goal is again possible. And it doesn't matter if you turn left or right, it's just important that you always choose the same direction so that you don't end up backtracking on yourself. You don't want to randomly select a direction. So we go this direction. Now we start following the contour of this obstacle. We get to here and we still can't go this way because the obstacle's in the way. We get to here, we still can't go directly towards the goal because the obstacle's in the way. Same thing here. We'd have to cut through the obstacle to go toward the goal, which is all the way up here. But when we get to this point here, we can then now again beeline on a direct path toward the goal. We detect an obstacle here, and even though it might be shorter to come around this way, we always turn the same direction and eventually find our way to the goal. this extremely simple algorithm is not always guaranteed to get you to the goal. So if you look at this second example, if we're always turning left, we will just repeatedly end up taking the same path and never actually coming in to get to the goal. So let's see if that bug zero algorithm would work for our given setup here. Here's our start location, and here's our goal location. This would be a good place to pause the video and see if you can come up with the exact same path that I'm about to show. Alright, well, applying our bug zero algorithm, our robot would start here and it would immediately rotate toward the goal. It would then go toward the goal. And for ease here, let's say that it always turns right. So it would follow up along this direction. Then follow the contour of the object, get to here, and beeline toward the goal. And let's say it misses the edge of that chair here. Turns right, turns right, and then it can get to the goal through this path. If you decided to have it turn left, when it gets to here, it would follow the contour of the obstacle, and depending on your exact implementation, it could keep crawling around to the left until it loops all the way around, or it could pretty easily get stuck by just trying to follow a path like this over and over. So depending on how complex you make this follow obstacle contours, it could get stuck in a cycle immediately here, or it could find its way all the way around to the goal this way. A slight improvement in terms of guarantees to get to the final goal is this second algorithm, known as bug 1. And for this one, you start out in the same way. You move toward the obstacle, so on a straight path toward the goal, until an obstacle is reached, and then you follow the contour all the way around until you get back to your original position. At that point, as you're going around, you constantly are noting, how close am I to the goal at each one of these points. You say, how close am I to the goal? And then after you get all the way back to your original position, you've marked that this is the closest point to the goal on this obstacle. So you backtrack to that point, beeline toward the goal, and do the same thing again. This one is guaranteed not to fall into that same trap of constantly going around the obstacle in the same direction. There are some cases where it doesn't work very well, so in this case, we go towards the goal, we go all the way around, get back to this point, realize that this point all the way back here was our closest, so then we have to find our all the way back there, and then we go to the goal. So that's not super efficient, but it does have better guarantees than bug 0. A third version of this algorithm is called bug 2. And just like with bug 0 and bug 1, it has its own problems. So for example, if we follow bug 2, we always move toward the goal until an obstacle is detected or the goal is reached. But now we follow an obstacle contour until the main line is reached again. So you always say, if I'm starting here and I'm trying to go to here, I'm going to denote this main line. Or on this one over here, this main line. So I get the obstacle, I follow the contour, when I get to the main line, now I jump off again. So definitely does better on some obstacles than bug 1, but on others it has a similar problem. So get to the main line, follow contours, and always turn the same direction. So in this case we're always turning left. So this one has some unfortunate side effects like the previous one as well, where we're looping back on ourselves and not finding the most efficient path. And that's because we don't do any sort of path planning. We don't realize that at this point it would be better to go right instead of going back left. So that's the real limitation of these bug algorithms, is they don't assume that you can do something more complex. They just follow very simple rules. And so that takes us to our next set of considerations here. I would say, do we need a complete plan? No, but really, yes. We're going to get much better results if we plan out our entire path ahead of time instead of trying to rely on simple heuristics. So to do that, we'll dive into these next considerations. The first being the configuration space. So it might not seem obvious, because for our simple differential drive robot that can turn in place with a 0-degree turning radius, our configuration space really is just the physical space. Meaning, if I'm here, I can get to any point around me without any extra motions. So if I'm here, I can get to any of these different points in any direction around me in a very continuous way without any extra work. I can get from one configuration to another very simply without having to go through a third configuration. That's not always the case. So let me just reiterate why that's the case here. It's because if I'm currently here and I'm facing in this direction and I want to move to here facing in this direction, I could do this in 3 steps. I could do a rotate. So that would rotate me around this point so that I can face the second point. And then I can do a forward motion. And that'll take me from this point to that second point. And then I can do another rotate so that I'm heading in the correct final direction. So that means I start here, I rotate in this direction so that I'm here facing this direction. Then I actually move from one point to another. And then finally, if I'm still facing this direction, I rotate so that I'm facing this final direction. I can do that in all a continuous motion. That is because we have a very simple device that's not technically holonomic, so it can't directly translate in this direction, but it can rotate in spot and then translate. It's the rotating in place that really gives us this advantage. But you might imagine something like an Ackerman steering style vehicle. So that would be like any sort of car or SUV or any sort of vehicle you may have driven. If you think about having your car, if you're currently right here with your 4 wheels, and I want to be right here instead, I'd have to drive forward and then reverse backwards. Meaning I'd have to go through this third configuration to get to that other point. And so that means that our configuration space is a lot more complicated. I can't get directly from here to this point if I'm facing in this direction. I might have to drive forward and then back into this point. And then again, if I want to be facing in a specific direction, it's not altogether obvious how to end up in that final direction. So you can be thankful that we're using this really simple differential drive vehicle. So we don't necessarily have to worry about calling this a configuration space. We can really just refer to it as our physical space. So our map is going to be a map of the physical space instead of thinking about it in terms of some other higher dimensional configuration space. And since it's so simple, that's all we'll say about configuration space for now. So let's move on to talking about safety bounds and how can we do that simply and computationally efficiently. Well, if my robot starts out here and then it starts driving and it ends up here right next to an obstacle, how do we know how close we can get to the obstacle without running into it, for example? We normally think about our robot in terms of its position, which is just an X, Y point in space. But if we were to zoom in on this point, if I were to consider this position as an XY coordinate, and in fact we can even think about it as a full pose with theta, because it depends on my rotation. If this thing were rotated around this way, this wheel would probably already be in collision with this obstacle. How do we handle this? Well, we have 2 options. we could do a really complex collision detection routine. So for those of you who've had game development with Prof. Osborne, he may have talked about how complicated collision detection can be, especially if you're talking about irregularly shaped polygons or even just rectangles. So the algorithm for seeing if one rectangle is colliding with another rectangle is actually not all that easy to come up with a mathematical formula for it, and it's not all that computationally efficient. So if you took that class with Prof. Osborne, he may have said something about bounding spheres, where we would put a sphere around all of our obstacles, sort of as tight of a sphere as possible, and do really simple collision detection among spheres, because that's really just taking the Euclidean distance between the center of the spheres, so this distance here, and then also considering the radii of the two spheres. So R1 here and R2 from those 2 points. And if that distance is less than R1 plus R2, then you have a collision. So we could do something really simple like that. Or we could do something simpler, which is more common in robotics. We could inflate the obstacles and shrink the robot. So really, our picture is going to look more like this. We are going to do this idea of having sort of a sphere around our robot, except it's going to be only used to inflate the obstacles themselves. So we'll put a bounding sphere around our robot and find the value for r. So you can think of this as the radius of the robot's bounding sphere. Then we shrink our robot to a point. That would be step 1. And in step 2, we inflate the obstacles. So zooming back in on this picture, we would have our point for our robot, and now all of our obstacles are inflated by the radius of the robot. That means we're not going to be getting as close as possible, because the robot itself isn't spherical. It actually fits in it would be tighter inside of a bounding rectangle. But this is going to be good enough, and most of the time we don't want to be getting right up against the edge of an obstacle anyway. So it adds a little bit of extra safety margin. In fact, based on the values for our sensors and what we think is a reasonable approximation for where we're at in space, let's say we think we could be anywhere off from 1 to 2 centimeters on position, we'd probably want to inflate this bounding sphere by even more. And then add that as the that radius on all of our obstacles. And so there are a few different algorithms for inflating obstacles. We can use what's called an offset edge approach. We can inflate the region around obstacles by a fixed amount, or we can actually take into account the shape of the robot itself. And I have a few of those implemented. And a little widget here to show them off. So in this case, if I, let's say, check the first one, this would be what's called an offset edge approach. And I can shrink and increase the size of this region. So this would be like the radius of the robot. This does have some disadvantages though. So for example, with really sharp corners, I end up with this extremely long spike, and clearly the robot could be within this region without much trouble. So that offset edge approach isn't used that often. Instead, what's more common is to use this inflation approach, where essentially we put like a little spherical bounds on all of your indices. And then a essentially offset edge from every edge as well. Finally, there are more complicated approaches where you take into account the actual shape of the robot itself. So if the robot's larger, the inflated regions gets larger. And if it's more narrow, you could see there's less space for this really narrow looking robot on the top edge and the bottom edge, but really wide spaces on the sides of the obstacle. Sorry, this is really hard to demo on an iPad. But I'll make sure to put a link to this in the chapter for this, the webpage for this chapter. All right, our last consideration is the actual representation of the map itself. And there are a number of different ways to represent your map, and I'll give a few of them, but we'll start with probably the most intuitive and simple approach, which is just called an approximate decomposition to cells. So in this case, this little blue blob here is our obstacle. And the grid around it is our physical space that we've decomposed into equal-sized cells. And the process is very simple. Essentially, for every cell in which you can find part of the obstacle, we just mark that entire cell as being impassable. And so if what we wanted to do was find a path from, let's say, for example, this location here as the start to a location over here as the goal, we would just hop from cell to cell, and we'll talk about how to find an efficient path in a few slides. Until we get to our goal. One downside to this approach that you might pick up right off the bat is that this corner here in particular is really only barely overlapping those two cells, but we still had to mark them as occupied. Well, what if the robot was small enough to fit through this gap? We'd have to have chosen a path all the way around. So a slight improvement on this is to use an approach with variable cell sizes. So in this case, some cells can be quite large because it's not really close to the obstacle. For example, these really large cells over here. And then some right around the corners are really tiny little cells. And there are a number of ways to approach this kind of problem. The most common is to just drag a line across from left to right until you hit the corner of something, and then start subdividing that space into different cells. I won't talk about that actual algorithm because we're actually just going to use this dumber version here just because it's simple and we're talking about a pretty small graph anyway. But if you wanted to map all of, for example, the Claremont College's campuses and have a robot drive around it, you'd want to have a representation that fit on a microcontroller a little bit better than something that had this many cells. So the nice thing about this approach is that if I were to say that this were the start location, and my goal was over here, and don't forget this is already the inflated version of the obstacle, my path can in fact go through the cells here across the bottom to get to the goal cell. So what would that look like if we did this approximate decomposition to cells for Edmonds 105? So here would be another good place to pause the video and see if you can think about what this picture would look like for our classroom. Well, we would basically just need to say any cells in which you find an obstacle, we need to mark them as occupied. So even for example, this first row, even though some of the other rows only take up 2 cells, this first row overlaps this cell, this one, and this one. So it's 3 cells over here in our occupancy grid. But now with this map, again, if we have our start location, and we have our goal location, you can find a path from one to the other without having to worry about these simple bug algorithms that have to take sometimes terrible paths to your target. Alright, so that is all we'll talk about in terms of map representations, just these really simple what are called occupancy grids. There are other versions, for example, a visibility graph, a Voronoi graph, triangulation methods, potential fields, and I'll give links to these different types of graph representations on the website. But I don't want to confuse people, and we'll just stick with our really simple occupancy grids for this class. And that's where this first video will end. In the second one, we'll actually talk about algorithms that take, for example, an occupancy grid like this. They start in a goal location, and then actually find the path. Which cells do you actually have to hop through to get from one to the other?